Hey guys, today we're going to talk about electric fields and electric potential. You already did some reading on this and you answered some questions from the textbook. So today we have this lecture. We're going to reinforce some of these ideas. I'm going to show you some simulations and then have you play with the simulations to help reinforce your own understanding. Then there'll be some review and then a quiz next week. Let's jump into it. So we finished off with example 6b, where we had these two particles, right? Two positive particles, or just two particles, and then we're talking about changing the distance between them. Now, example 7, we're picking up the same set of notes that we were working with before, but now we're going to finish it. Imagine you've got two negatively charged particles, and they're originally 2 meters away from each other. Okay, so they're negative, so they're pushing away from each other. What will happen to the charges if they are allowed to move freely and there are no other forces acting on them? Well, they're pushing away, so they're going to accelerate away from each other. And they will always be pushing on one another. Even as they get farther apart, there's still a force, even though it's very small. Here's the key thing to note, that the force between them is now resulting in them moving. And now we're going to relate this to energy. So what's resulting? We're ending up with kinetic energy. Where did the kinetic energy come from? It came from the fact that those two particles were pushing on each other. That force then creates electrical potential energy. If we think back to gravitation, right? We lifted something off the ground, and then the gravitational force resulted in kinetic energy. So there is a gravitational potential energy. Same thing with a spring, right? You compress the spring, and that results in kinetic energy. Same thing here. The electric force produces now a new kind of potential energy. And so that's example 8. Do these charges have potential energy? The answer is yes, they do. As long as two particles are near each other, then they have the ability to push off each other and create kinetic energy, and that's what we call potential energy. So now imagine two negatively charged particles originally 2 meters away from each other. Someone moves them closer. Right? So if you move them closer, are you doing work on them? And the answer is yes, you are. Why? Because you're having to exert a force over a distance. Remember the equation for work. Work was force times displacement times cosine theta. Right? In here, there is force and there's displacement as you push those two particles closer together. So in order to bring two particles together that don't want to be near one another, you have to do work. If you think of something that's on the ground and you lift it, it wants to be on the ground. You can think of it that way as an analogy. But if you're moving it away from where it wants to be, you're having to do work, force and displacement. And that's what's happening here with these two particles. Another scenario, two negatively charged particles originally 2 meters away from each other. Someone moves them closer together. What's happening to their potential energy? Okay, so now we are doing work to bring them closer together. Now they're closer, there's a stronger force, and there's more distance for them to push apart when they're let go. So if you do positive work, you're adding potential energy to the system. And that's like we saw in the bar charts. So there's a certain amount of potential energy, then there's some work done. Now there's more potential energy as a result. So now to talk about fields and how we visualize all this stuff. A gravitational field is very simple. There's a massive object and the field lines all point inward. The reason we come up with fields in the first place is to explain how objects can exert forces on one another from a distance. Again, this still is very difficult to understand. Scientists are not really sure they understand it. But if two objects are exerting a force on one another and they're not even touching, well, then how are they doing that? Scientists came up with this answer. They said, well, one object creates a field, and then the other object is interacting with that field, right? Not necessarily interacting directly with the other object. So the field is a way of helping us conceptualize what's happening and how two objects can exert forces on one another from a distance. In gravitation, everything is attracted, so everything creates, you can imagine it as a sheet, everything in gravity is like a hole, and everything's going to get pulled into that hole. So arrows only point towards the object. Arrows point downhill, right? If you have the sheet, this landscape with a hole, the arrows all point downhill. And as the lines are closer together, then it's a stronger force. Electric fields are different though. In electric fields, you can imagine that positive charges, a positively charged object is a mountain, and a negatively charged object is a hole. I want to show you one of the simulations. You see under the Unit 4A page, under simulations, there are these links. And here's one where you can change the mountain and you can change the hole by adjusting the amount of charge. More charge means a bigger mountain with a wider base, steeper slope. And same thing for the negative. And you can make the positive negative, and so you can have two holes or two mountains, whatever you want it to be. Now those blue lines going around, those are altitude lines. So if you were to walk around that blue line, then you would not be changing altitude. You'd be staying at the same altitude. And that represents the potential energy. But if you were at that point, if you went from one point to the next, you'd be changing your altitude, you'd be changing your height, and so you'd be changing your amount of potential energy. You can think of it kind of like gravitational potential energy, just changing your height. And here are the rules. Lines go away from positive and towards negative charges. The density of the lines indicates the field strength. More lines, stronger field, which also, if you're thinking about this landscape model, means a steeper slope. So the field lines tell you the direction and strength of the force on a positive test charge. So if you were to take like a little positive charge and put it in there, it would tell you the amount of force and the direction of the force on the positive test charge. And so a single positive charge looks like this. All the arrows are moving, pointing away. A negative charge, all the arrows are pointing in. And you can imagine that negative charge is being down in a hole, and all the arrows are pointing downhill. Okay, if you have two positive charges, this is what it looks like. Those field lines point away from each other. Right? And if they're equal positive charges, they have equal lines, equal number of lines coming off them. A positive and a negative charge, equal magnitude though. So all the arrows are pointing away from the positive and towards the negative. And field lines never cross one another. Never cross. If you have two oppositely charged plates, this is a very, very common scenario in electrical devices that we're not going to get into much. But you have positive on one side, negative on the other, and now you have a uniform field where it's kind of the same throughout in the middle, pointing from the positive to the negatively charged plates. This simulation is great for seeing what it looks like when you change the charge on an object and seeing what the electric field lines look like. So you can see if one is 0 and one has some charge, then it's just the lines radiating outward. If you make it positive or negative, the lines point away or towards the object. And then what the lines look like if you've got two charged objects, how they curve and go from one to the other. In the PhET simulation, you can create your own landscape of charge, but you should turn off the electric field arrows, and then you can turn on voltage. And what the voltage shows you is the elevation, and it shows it to you with red and blue light, and it shows it to you with the intensity. So the more intense that light, the higher or lower it is. And so you can imagine the positive, the red, has a positive altitude, and the blue is a negative altitude. So the blue is a hole, and the red is a mountain. And what I'm doing now is I'm marking the voltage, the potential line. So that's elevation, right? As I get closer and closer to the blue, I'm going lower and lower. And so those are, if you walked around one of those green lines, you would be staying at the same height, at the same altitude. Right? So that's going deeper and deeper into that hole. The green line in the middle is 0. It's the 0 elevation between the positive and the negative, the mountain and the hole. You can see I'm marking every 5 volts. So that's like changing your height by 5 meters or something like that. And then the fun thing to do here is to create your own landscape with lots of different charges, and then put the altitude reader, the voltmeter, in there, and mark off the altitude at 0 and then at every 10 volts. So again, between each line, if you're going from one line to the next, then you can see you're changing your elevation. Right now I'm marking the mountains going up in the red regions, right? And you can see that there are some places where the lines are really close together. That means it's really steep at those spots. That's where the electric field would be the greatest. The electric field is the steepness. The potential, the electric potential, is the height. So I'm marking the different heights. And again, if you were to walk around on any one of those green lines, you would just be moving at the same altitude. It's like an altitude topographical map. And I encourage you to find this simulation and play with it yourself. So I hope this video helped you understand some of what we're studying, and make sure you turn in all the work for this week, and hopefully we'll see you soon.